Good morning to everyone. I am Shivraj S.J., Assistant Professor of Civil Engineering Department, BVRIT Narsapur. I am dealing with the subject called that is design and drawing of RC structures. This is one of the very most important subject in the civil engineering profession. And the prerequisites required for this subject is the knowledge on engineering mechanics, and the knowledge on strength of materials, and also the knowledge on structural analysis. With the knowledge on these three subjects, we can able to design and draw the structural elements of RC structures. In that, now we'll discuss particularly in that unit one. So the unit one is limit state method of design and serviceability. And that the first topic is introduction. So we'll move to the introduction. Before that, so what is structure? See, structure refers to an system of connected parts used to support loads and loads or forces. See, in that the example for structure is like buildings, bridges, and towers. So these are all the examples of structures in civil engineering. Again, in buildings, the structure consists of walls, roofs, foundations, and in bridges, the structure consists of a deck, supporting system, and foundation. Again, similarly, in the towers, the structure is nothing but the vertical elements, horizontal elements, and diagonal elements. So along with this foundation, these are all the particular parts of a particular civil engineering structure. Again, a structure can be broadly classified as a substructure and superstructure. See, the substructure is nothing but the portion of a structure which is below the ground level is called substructure, and the portion of the structure which is above the ground level is called superstructure. The example for the substructure is foundation, and the plinth, walls, columns, floor, slab, beams. So these are all the examples of structural element which is above the ground level, that is superstructure. So now, as you are seeing, these are the typical examples of structures which are done with the RC material. Now we'll go to the advantages of reinforced concrete structures. In that, the first advantage is like there is a good bond between steel and concrete. Since the concrete is very good in compression, whereas steel is very good in tension, so both will act together and will bear the stresses simultaneously. So there is a very good bond between the steel and concrete. And also with the help of RC structures, we can have a very stable and durable structures. And these RC structures shows very less buckling, and like the structural members having showing a very better buckling strength against buckling. And also the structures with RC structures can have a very good aesthetic appearance also. And the structures with the structures with RC elements shows a very less corrosion because the steel is embedded into the concrete. So these are all the advantages of having reinforced concrete structures. Next, we'll move to the like what is the importance of steel as a reinforcement. As we all know that since concrete is very good in compression, it only takes the compressive stresses. But simultaneously in a particular structure, so there is the tensile stresses or tensile forces which is also exist in a particular structure due to the loads. So in that condition, we need the tensile material such as like a steel. So this is what it is required in achieving both in bearing the tensile stresses of a particular structure. So as we know that the steel, since steel is embedded into the concrete, so it is having very high relative strength, and it is having high tolerance of tensile strain, and also it is having very good bond to the concrete, and irrespective of pH or moisture and similar factors. And this steel is also having a very good thermal compatibility, and also it shows very good response to changing temperatures. And steel is having very good durability in the concrete environment, so irrespective of the corrosion. So these are all the importance of a steel in RC structures. Now we'll move to the applications of RCS. Like RCC is deployed in columns, beams, footings, slabs, etc. So likewise, the RCC is also applied or in storage structures like dams, water tanks, tunnels, etc. And also, with the help of these RC structures, we can also construct the bridges, walls, towers, underwater structures, chimneys, cooling towers, shell roofs, folded plates, and tall structures and skyscrapers. So these are all the main typical examples of with examples of RC structures. With the help of RC structures, we can have any shape of the structure, and also it shows robustness in the element, and the RC structures having very flexibility in construction. And with the help of RC structures, we can achieve very rigid joints, and also will have very ease in the design also. So the only thing is that the only difficult part in reinforced concrete structure is like a detailing, and also the reinforcement congestion. See, since if any particular structural element consists of more reinforcement, in that the concrete that the pouring of concrete, the area becomes very less. In that, this is the one of the problem we are going to experience. So these things we have to take care in achieving constructing any particular structural element. And also simultaneously, for the concrete, we can also have some difficulty in shrinkage, creep, and corrosion. So we should have a proper care in having these kind of difficulties in concrete. So next, we'll move to the deflection, importance of deflection in RC structures. See, any RC structural element is designed due to the vertical loads such as dead loads and live loads. So simultaneously, not only to the vertical loads, the RC structures are also designed for the lateral loads such as wind and earthquake forces. So these, keeping into consideration of these deflection criteria, the RC structural elements are designed, and it is executed properly. See, as you are seeing in this, the performance-based design, it is what the performance-based design, and the control of displacements are within the acceptable limits during the service loading, and factored load, and also varying intensities of environmental loading. Now we'll see the code books used in RC structures. See, this is what the code book, what you're seeing, the IS 456-2000 is the code of practice for plain and reinforced concrete structures. So earlier we used to have IS 456-1978. So after 1978, the revision is in the 2000, in the year of 2000, it is made a revision again. So right now we are using this IS 456-2000, and this is used for the, and this code gives certain suggestions and guidelines in designing any particular structural element. Next, this is also one of the code, like IS 800-2007 is used to design a steel structural elements. So this is one of the code, and simultaneously IS 875 codes is used for the loads. So in that, particularly part 1 deals with the dead load, and part 2 is deals with the live load, and part 3 deals with the wind loads, and part 4 deals with the snow loads acting on the buildings, and part 5 is for special loads and combinations acting on a building. So these all are IS 875 part 1 to part 5 deals with specially about the loads. So by having considerations from these code, will consider the loads in a particular structure, and then will design accordingly. And one more last code, that is IS 1893-2002. So this is what the code is used for the earthquake resistant design of structures. And right now we are having the revision of this code, IS 1893 in the 2016. This code has revised in the very recently in the last year. So still we are using that code. But anyhow, we should use both simultaneously as per accordingly the design of structures, RC structures. So this is about my topic. Thank you.